All right, today we are continuing our lessons with function composition, which is where you plug one function into another, and we are specifically going to look at what happens when we do this with absolute value functions. So if I have some function and an absolute value function, and I do composition either way, for what values of x do you think that the two functions will have the same outputs, the same y values? Well, that's what we're going to explore. Starting with this first function, p of x, this is a linear function that I have shifted down 3 units and vertically dilated by 1/2, or it has a y-intercept of -3 and a slope of positive 1/2 is probably how you've seen this graphed more often in your math career. I'm going to go ahead and graph this in blue. So starting at -3, up 1/2, up 1/2, over and over, until I have enough points to connect the dots, and I'm going to use a ruler to make sure that I can get this line as straight as possible. So there is our p of x, our blue graph. What we're going to look at now is, let's say a of x is the absolute value of x, and h of x is equivalent to a of p of x. So that means h of x is a of p, which means I'm going to take my a function, and instead of plugging in some number, I'm going to plug in 1/2 x minus 3. So what that will look like, since this is the absolute value function, it will be the absolute value of 1/2 x minus 3. This is h. Now I want to get this on the graph, and I'm going to do that in red. This one is not a linear function, so it's not as easy as finding the y-intercept and plotting my slope. So what I'm going to do to help myself graph this is make an xy table, find some points on the graph, and then I can connect the dots. So starting with a few, I'm going to go from right to left, sort of. So I'm going to start with 8. And again, I'm plugging them into this function here. So 1/2 times 8 is 4. 4 minus 3 is 1. The absolute value of 1 is 1. 6, 1/2 times 6 is 3. 3 minus 3 is 0. The absolute value of 0 is 0. 4 times 1/2 is 2. 2 minus 3 is -1, but the absolute value of -1 is positive 1. Going to keep with even numbers. 2 times 1/2 is 1. 1 minus 3 is -2. The absolute value of -2 is positive 2. And then 0, 1/2 times 0 is 0. 0 minus 3 is -3, but the absolute value of that is positive 3. So I'm going to plot these and see if that gives me a good idea of what is taking place here. And knowing that my absolute value function has a V shape, I can see that here where it switches directions is my vertex. And so there is my composed function h of x. So the next part of our lesson is asking us to graph it, which we've done. Now for what values of x will h of x be equal to p of x? Now remember, p of x was our blue graph and h of x was our red graph. So where are they equal? Where are their y the same? Well, this is where they are overlapping, and that is from when x is 6 and greater. So that is for values where x is greater than or equal to 6. So to describe the relationship between these two graphs, I can start off by saying that p of x and h of x are the same when x is greater than or equal to 6. All right, and now I need to look at what is happening when x is less than 6, so the left side of my graphs. Well, I can see that these are similar, and they look like mirror images of each other, which we call a reflection. So this is a reflection across my x-axis. So when x is less than 6, they are reflections of each other across the x-axis. And remember, the x-axis is the horizontal line, y equals 0. And that is for our values when x is less than 6. Okay, so keeping p of x in mind, we are still going to look at that on the next page. And in fact, I'm going to go ahead and get that graphed in blue again. starting with my y-intercept at -3, connecting the dots. Okay. Now, with a of x still being the absolute value of x, what we're going to look at now is a new function k of x that is equivalent to p of a. So what we're going to do is composition the other way around, and I'm going to take our linear function p, and instead of plugging in some value, I'm going to plug in the absolute value of x. So that's going to be equivalent to 1/2 times the absolute value of x minus 3. This is my new function that I'm going to graph in red, and again, I'm going to make a table to help me find points on that graph so that I can connect the dots. And I'm just going to kind of go from right to left again, starting with 8. The absolute value of 8 is 8. 8 times 1/2 is 4. 4 minus 3 is 1. 6, the absolute value of 6 is 6. 6 times 1/2 is 3. 3 minus 3 is 0. For 4, the absolute value of 4 is 4. 4 times 1/2 is 2. 2 minus 3 is -1. For 2, the absolute value of 2 is 2. 2 times 1/2 is 1. 1 minus 3 is -2. For 0, the absolute value of 0 is 0. 0 times 1/2 is 0. 0 minus 3 is -3. Getting into the negative territory, -2. The absolute value of -2 is +2. 2 times 1/2 is 1. Excuse me. 1 minus 3 is -2. For -4, the absolute value of -4 is +4. 4 times 1/2 is 2. 2 minus 3 is -1. I'm going to go ahead and get these points on my graph just to see where this leaves us. So those first 5 points are all matching with my original graph, but then here, -2, -2, and -4, -1 is where it changes direction, which is what we should have expected with our absolute value being in there. We get a V shape. So there's the left side, all matching up with the blue. And then here is our, excuse me, that was the right side. This is the left side. So again, looking here where our blue and our red overlap, that is when these values are equal to each other. That happens when x is greater than or equal to 0. So to describe the relationship between the graphs, we again can say that p of x and k of x are the same. When x is greater than or equal to 0. And then looking when x is less than 0, again, I can see that these are mirror images of each other, a reflection, but it's no longer at the x-axis where y is equal to 0. It is happening here along the horizontal line, y equals -3. So they are still reflections of each other, but at a different spot. Okay, moving on. Now we have a new function, and it is a quadratic. Quadratics are easiest to graph when they're in vertex form, so I'm going to convert this to vertex form firstly. Remember, -b/2a will give you the x-coordinate, and then plugging that value into your function will give you the y-coordinate for your vertex. So here, b is -2, so -2 divided by 2 times a is 1. That gives me 2/2, which is 1. Then to find q of 1, I will do 1 squared minus 2 times 1 minus 3. And 1 minus 2 minus 3 gives me -4. So my vertex is at 1, -4. And now I can write q of x in vertex form, which will be x minus 1 squared minus 4. And I'm going to graph this in blue. And I can go ahead and immediately graph my vertex, but I'm going to need to make a table to find some other points on this graph, my parabola. So going from right to left, I am going to start with 4. 4 minus 1 is 3. 3 squared is 9. 9 minus 4 is 5. For 3, 3 minus 1 is 2. 2 squared is 4. 4 minus 4 is 0. For 2, 2 minus 1 is 1. 1 squared is 1. 1 minus 4 is negative 3. We already know what 1 gives us, so let's go with 0. 0 minus 1 is negative 1. Negative 1 squared is 1. 1 minus 4 is negative 3. I'm going to skip ahead to negative 2. Negative 2 minus 1 is negative 3. Negative 3 squared is 9. 9 minus 4 is 5. So that gives me a good amount of points to get on my graph here. And I can connect those dots as best as I can. And there is my not perfect parabola. But nonetheless, a of x is still the absolute value of x. So let's find m of x, which is going to be equivalent to a of q. So that means I'm going to take my a function and plug in q of x, which is x minus 1 squared minus 4. So that's all going to go inside my absolute value. So here's our new function that I am going to graph in red. And again, I'm going to make a table to help me with that. So going from right to left again, I'm going to start with 4. 4 minus 1 is 3. 3 squared is 9. 9 minus 4 is 5. The absolute value of 5 is 5. Going to 3. 3 minus 1 is 2. 2 squared is 4. 4 minus 4 is 0. The absolute value of 0 is 0. Moving on to 2. 2 minus 1 is 1. 1 squared is 1. 1 minus 4 is negative 3, but the absolute value of that is positive 3. For 1, 1 minus 1 is 0. 0 squared is 0. 0 minus 4 is negative 4, but the absolute value of that is positive 4. For 0, 0 minus 1 is negative 1. Negative 1 squared is 1. 1 minus 4 is negative 3. The absolute value of that is positive 3. I'm going to jump ahead over to negative 2 just to see what that brings us to. Negative 2 minus 1 is negative 3. Negative 3 squared is 9. 9 minus 4 is 5. So I'm going to go ahead and start graphing these points. Those two are matching so far, but that next one gives us something different. Different. Negative 2, 5. Okay, so we've got some discrepancies here. It's not totally lining up with the blue, and I need to figure out truly what's happening here. So I'm going to go ahead and plug in negative 1. Negative 1 minus 1 is negative 2. Negative 2 squared is 4. 4 minus 4 is 0. The absolute value of 0 is 0. So now I also have a point here. So this is my composed graph. We've got two parts where the blue and the red overlap, and then a part in the middle where they are different. So where are they the same? Well, on the right-hand side, that's when x is greater than or equal to 3. And on the left-hand side, that's when x is less than or equal to negative 1. So when we're describing the relationship of these graphs, we know that they are the same over those two intervals. And then I need to figure out what's happening between negative 1 and 3. Well, if I'm looking again here, these two are a reflection of each other, a mirror image across that x-axis again. So they are, again, are reflections of each other. Over the x-axis, which is that vertical line, y equals 0, when x is between negative 1 and 3. Okay, I'm low on time, so I'm going to record the last part in a separate video.